Okay, hello everyone and welcome back. Today we have a new batch of exercises about matrices and specifically more about invertibility. And there is also one exercise on these error correcting codes. We'll come to it later. So let's just start. The first exercise gives us two matrices and asks us to invert them if possible. And then we have to solve a linear system. So how can you invert a matrix? Well, you can use the Gauss-Jordan elimination even here, because if you write this big matrix where you have and here you put the identity matrix, so 1 1 1 here, 0 0 0 0, and then by doing the allowed moves on rows, we know when we do the Gauss elimination, we can try and transform this part to an identity matrix, and here with this after this set of moves, we'll end up with what will be the actual inverse matrix, and this is an algorithm which allows you to actually invert a matrix just by using this Gauss elimination. So we start, and yes. So first, let's see. I have this one, and so I try to get some zeros here, and so yes, I multiply by suitable numbers the second and the third row. So I have 3 minus 3, 6. This is not doesn't change, but here I multiplied by 3. Okay, here I multiply by this is times 3, and this is times. Okay, so again here this very good. Then I can subtract, or actually add, so replace this with the second plus the first and the third plus the first, see what happens, and which would be minus 3 1 minus 3 1 0 0, and here it's the second plus the third, the first, so 0. Well, sorry, this is okay 0, and then minus 2 3, and then this is 1 3 0, and here the same thing, so 0. Here what you have is, I think, 5 over 2. Here you have minus 3. So here you have 1, 0, and this. Very good. Okay, so let's just multiply by suitable numbers so we can rearrange a little bit and avoid fractions, which is sometimes kind of annoying. 0 5 minus 6. Have to be careful not to make mistakes here. 2 0 3. Okay, then then what we want to do is like eliminate this. So what is it? Let's multiply the second by 5. Yes, I think so. Yes. Okay. And for now, let's take this. Minus 5. This. Okay. And then here nothing. Hope I'm not mistaken here, but okay, let me just copy this. Okay, very good. Okay, so I should be okay. Yes. Now I can just replace the third by the sum of this with the second. And okay, 3, 1 minus 3, 1, 0, 0. And yes, so here it's 0, 0, minus 6 plus this, which means minus 12 plus this. So it's like just this, 3 over 2. Okay. It's very likely that I'm going to make some mistakes at some point, unfortunately. So this is, I think, 9 over 2, 15 over 2, and 3. Okay? Okay, fine. We're not done yet, because we want also to remove this and these things. So we need something more, actually. So what should we do now? Let's multiply the first by 5. So this. And the others, let's keep them. Okay. And yes, for now, let me just keep this. Don't want to rush. Okay. Then you can replace with the sum. So what happens? No, sorry, not the second, but the first. So here doesn't change. Here you get 0, and here you get minus 15 plus 15 over 2, which is minus 30 over 2. It should be minus 15 over 2. Is it? Let me check. Seems so. Seems so. Yeah. Very good. Then the sum. Okay, so it's 5 plus this, which means 15 over 2. Exactly. And here 15 over 2, 0. Okay. Okay. Looks good. Minus 5. Doesn't look too bad. Okay, which now get this. We are not done yet. What should we do now? First, let's just remove the fractions, multiplying accordingly. So this is minus 15, 15, 15, 0. That's wrong. Okay. 0 minus 10, 15, 5, 15, 0, 0, 0, 3, 9, 15, 6. This is it. And okay, then. Okay, very good. I can also simplify a little bit, namely divide by 15 here, the first row. So we get minus 2, 0, minus 1, 1, 1, 0. And here we can divide by 5. 0, minus 2, 3, 1, 3, 0. And here we can divide by 3. 1, 3, 5, 2. Yes. Very good. And then what we have, what should we do now? We should remove this and this, but it's kind of easy now because we can replace this row by a suitable multiple of this one and also this. So for example, let's replace this by the third plus the first, and here by the third, and here let me see, that would be the second minus 3 times the third. That's a possibility. And here as before, so this doesn't change. Hopefully it's correct. And okay, and yes, so I have to take the second one and subtract 3 times the third. So this is going to be 0 minus 2. This is going to be 0. That's good. But here, be careful. 1 minus 9 is minus 8. 3 minus 15. It's going to be minus 12. And 0 minus 6 is going to be this. Okay, very good. Very good. And here we finally, here we have to change. So we just add the third. So it's minus 2, 0, 0. And then 4, 6, 2. Okay, looks good. And now we're almost done because we just need to make these numbers become ones. So we just multiply accordingly. And so we get 1, 1, 1 here. Okay. And here we just divide by minus 2. This is minus 2, minus 3, minus 1. and this has to be 4, 6, 3, and this is 3, 5, 2. And this is it. This is how you get the inverse matrix of your given matrix. And okay, I'm just checking myself if it's correct. Okay, looks fine. Looks fine. So this is the actual inverse matrix. Okay. Okay, let me add a page. How can you do? Okay, so very good. Okay, let's go on. So let me just write the inverse matrix. Now we have it, and it's this. Very good. Okay. Minus 2, minus 2, minus 1, 4, 6, 3. Okay. Okay. We also need to find the inverse of this other matrix, BT, which is again 1T, 1 true. Okay, 1T, 1 true. Okay, and fortunately this is just 2 by 2 matrix, so it's a little bit easier. And so again, in the same way, you put the identity here. Now we have a parameter. We have to be careful at some point, but let's start and see what happens. So here it's kind of easy. We just subtract the first. So this is 0, this is 2 minus t, this is, be careful, minus 1 and 1. Okay. Okay, very good. Now before dividing by this, we had this thing. At some point we'll have to divide it. To divide by this thing, but let's not do this. Instead, let's try and remove this, if we can make it. Can we make it? Well, perhaps no. Perhaps no. So okay, no problem. Let's just assume that now t is different from true, so we can divide and get this. This is a 1, and this is minus 1, 1. Okay, very good. And now we can try and remove this. So we replace this 1 by this minus t times the second. So this is going to be 1, 0, and then 1, 1. Let's hope I'm not wrong here. 1 plus t over 2. This, I think. And this has to be minus t. Okay, looks pretty much fine. Let me just make this thing computation here. It's going to be 2 minus t plus t, so it's going to be 2 over 2 minus t here. Okay. Okay, very good. And I mean, we're actually there. So minus 1, 2 minus t, 1, 2 minus t should be the correct matrix. This, assuming that t is different from true, this should be the inverse matrix. we want to be sure. If we want to be sure, then let's just check that this works. So let's just multiply this by this, and let's see if it's really what it has to be. At least on this part. So here you have 2 minus t. So this with this and this with this, so plus minus t. No, this is 1. This is a 1 minus 1. Okay. Hopefully it's correct. Let's just compute this. We can see. Wait a minute. Did I make something wrong? Let me see. It can well be, it's part of the game. You can make mistakes. You can easily make mistakes while computing stuff. No, this is a t, of course. This is a t here. So let's compute this. This is actually 2 minus t over 2 minus t, which is 1. It looks good. It looks good. That's correct. That's fine. Looks good. Here, let's hope that here we have a 0. So take this minus t plus t, which is indeed a 0 here. And here I hope we have a 0 again. 2 minus 2, it is. And here we should have a 1. So this minus t plus 2. Yes, it works. Yeah, it seems it's correct. We just checked one side, but yeah, it's actually enough to check this one side. I think, I believe. Oh, at least it's okay. It's okay. So yeah, we found the inverse, assuming that t is different from 2. bt is then minus 1, is then this thing. Okay. So, and what happens if t is equal to 2? Then let's go back to the passage just right before here. So we substitute. We get 1, 1 then 2, then 1, 0, and then here this is 0, 0, minus 1, 1. So you see here that there's no way we can go on with the algorithm, in the sense that we would like to put a 2 here, but there is no way we can do this. Actually, this here the algorithm stops. So in this case, the matrix is not invertible. Is not invertible. Very good. So we have something more to do. So we have this b, and we have to solve the linear system a x equal to b. So let me just add another page. So b was 1, 0, 1, and we want to solve ax equal to b with the other one. But here, we made such effort to compute the inverse. I just copy it. The inverse of a was this thing here. Where was it? So yes, it is here. Let me just copy it. This nice thing. Copy, and then put it here. So we know that if we have an invertible matrix, and then to solve a system like this, we have precisely one solution, and it's given by x, given by this, a minus 1 applied to b. So you just have to compute this thing. So good, and this, and the IT is what it is. I mean, it's going to be, I hope I'm not making mistakes. So it's minus 2 here, and then minus 1, and this is 4 plus 3, and this is 3 plus 2. So it's going to be minus 3, 7, 5. Well, this is it. This is the solution you want. So first you've made a lot of you've made a big effort to compute the inverse, but then you can use it to solve the linear system in a very straightforward way. And this is it for the first exercise, which was I think quite boring, but yeah, hopefully the following exercises are going to be a little nice. Okay, this is a little more theoretical. So we have a matrix which is of this form, it's a block matrix. So you have an identity, a big identity matrix here, another big identity matrix here, and some matrix here. And we would like to understand what is the inverse. So there is a hint, and the hint is as follows. So let's compute the inverse of this matrix. So how do you compute this inverse? Well, let's just try and compute it with the method that we used before. And I mean, it's kind of easy, fortunately, here, because we have to just remove the a. So just replace the second by this minus a times the first. It's perfectly okay. And here get the 0. This here, it's the same. This is 1, and here you have minus a and 1. So you have it. This is the inverse matrix. And indeed, if you do like here, just to check, if you compute here, this is going to be 1, this is going to be 0, this is going to be indeed minus a plus a, 0, this is going to be 1. It's correct. So you have this, and if you have a block matrix, you can somehow treat the blocks as they were numbers to some extent. So you can check that if you take I p, let me see. You're just mimicking this. Yeah, I think it works. Let's see. The block multiplication works like matrix multiplication, as we know. So we have identity minus 0, so this IP. This is going to be 0. The orders are okay. So minus a plus a is 0. Minus a plus a. And here you have 0 plus IQ times IQ, which is again the identity matrix of order Q. It works. This is it, and nothing more. That was very quick compared to the last one. It will be also very easy to write down. Okay, here we have something a little different. Namely, we have a error correcting code. We have this 1511 linear binary Hamming code with this parity check matrix. You see here the columns of this matrix are made in such a way that each one encodes a number in the binary form. So, for example, if you want this can be the number 1. the number 2 is then this one. Then you have at some point here the number 3, and so on. So you have all the numbers from 1 to 15 here. Okay, very good. And 1511 means that you have the message you have, the original message has 11 digits, but it's been decoded using the suitable generator matrix as some longer string of binary numbers. But there we assume there is an error, and the nice thing here is that we can find where the error is. So the idea is as follows. So see here, the way H is built is of this form, which is you have some matrix A here, and then you have the identity of order 4. Here is 4, 4. Here you have 11, 4. So what is the generator matrix? It's defined as this. It has to be a matrix. Has to be such that when you do H times G is equal to 0. And so yes, so it's going to be something like I4. So this is 15, 4. So we have to be something like here 11 and 15. So here we have to put the identity of order 11, and then you're left with a 4 times 11 matrix, which has to be minus A. And indeed, if you do the block multiplication, it's going to be A minus A, which is 0. Now, there is something else we have to say here. Namely, we are just having matrices with zeros and ones, and the rules of multiplications are such that 0 plus 0 is again 0, but 1 plus 0 is 1, but 1 plus 1 becomes 0. So it's like, they're not real numbers, they're just zeros and ones, and they are added and multiplied in a suitable way. So this and this. So it's the so-called field of true elements. I mean, no worries. It means it's even easier than working with the ordinary numbers. Namely, in that setting, you see that if you have a matrix of zeros and ones, and you would take the minus A, then this is actually itself, because if you do A plus A, then you would get 2 times A, but 2 is indeed 1 plus 1 times A, and that would be 0. So actually, to compute the negative of a matrix, you just have to take itself. They are just made of zeros and ones. Or if you want, you can just identify minus 1 with 1. So the same thing happens. So here you actually have A and whatever. So the point is that if you have a message B, okay, and it's being decoded, so this is what the problem calls W. Very good. B is has 11 what is it? Has length 11. Very good. And it's decoded, and now it has this has length 15. But I mean, the point is here, if the if the transmission is correct, then you do HGB and you get 0. But in this case, we know that it's not correct. So we'll actually get, after the transmission, some message, which is going to be this V, and it's not correct. We have just one error, just one. How do we know where the error when the error is? Well, we have to think a little about this. Say you have just one error, so V in this case is just this string of zeros and ones. Say you have some error, we don't know where, but this means that something which is 1 is instead a 0 in the correct transmission. So it means that if W is the correct one, then V and W differs by just something like this. This is just the vector which has all zeros and one and just a 1 at some position, recalling that if you do 1 plus 1 you get 0, and if you do 0 plus 1 you get 1. So if there is an error, just one error, this is going to be where you can find it. And actually, if you apply then the H matrix to V, then the H matrix applied to W is 0 by definition, because this is the correct message. And then you're left with H times this vector here. But you know, this is a kind of special vector which selects just the, say this is at position at some position k. This is the kth column of H. So the point is, we have to compute this H times V, and we know we will get some vector which will be some column of the matrix H, correct? And then we will know that the message had an error at that specific position, and we can correct it. So let's just do this computation. I hope the explanation was okay. This is going to be a very long computation. So let's do it. Let's do it. So it's well, it's very. Let's see if I can find some. Okay, so that was 1 1 1 1 1 1 1 0 1 1 0 1. Sorry, 1 0 1 1 0 1 1 1 1 1 0 0 1 0 1 0. Is it correct? Yes. 1 0 0 1 0 1 1 0 0 1 0 1 0 0 1 1 1 0 0 0, and then you have the identity here, fortunately. The identity. It's very long. And then you get this very long vector, which is 1 0 0 1 1 1 0 1 0 0 1 0 0 1 0. Well, it's very boring, actually. It's very boring. Yeah. Well, let me for this time just cheat a little bit. So let me just assume that this computation has been done by some very long computation, or if you have a computer, you can use a computer in this case. I mean, it would be very boring to do this by hand. So you can find out that this turns out to be 0, 1, 1, 1. So let's accept this. Let's just accept this, and just look at this matrix. It's if you look at it, it's just the fifth column of the matrix. So what does this mean? It means that there was an error. The error was at the fifth position. So we know the correct message. The correct decoded is what it is. I mean, it's just change the fifth. Just change the fifth number. So it's W1001 is a 0 here, and then it's the same. So 1 0 1 0 0 1 0 0 1 0. What I mean, it is what it is. It's not really important. So the fifth place, that was a 1 before. So here, see this. So we changed it, and we have a 0 instead. So this is the correct decoded message, but then you want to know something more. Let me just see if it's okay. It seems to be okay. So we want to know the original message. The original message, so it is this B such that G GB is equal to W. I mean, in principle, we would have to solve a linear system, but fortunately, the way G is defined, it is like this. So it has I11 here and then something more here. So if you apply anything to this, like let's say it's a B1 to B11, okay, then you see that you get some W, but it's immediate to say, we see, since here you have the identity matrix, then you have something which is again B1, B11 here, and then there is something else, and this is W. So actually W in the end is just the first 11 digits of B is just the first 11 digits of this thing. So it's indeed, you can conclude that B is just the first digit. So 1, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Should be okay. So should be this 1, 2, 3. Should be okay. Okay, 0, 1, 0, 1. Okay, this is it. And that's how you do this kind of exercises. Okay, let's go on. And so this is a little more theoretical, but yeah, it's about invertibility. So have to prove some statements. So we have to give some proofs of these statements. So we start with a matrix A such that A squared is equal to A and it's invertible. And it has to be, and we want to prove that it has to be the identity matrix. So why would this be so? Let's see. So let's take our A and assume that it's actually A squared. So, and A has an inverse. Okay. Okay. You can multiply by its inverse to the left, for example, here in this equation, and you would obtain what? A minus 1 times A2 is equal to A minus 1 A, and this is by definition the identity matrix. Okay, but here, what you have here is actually the matrix A, because like this matrix multiplication, if you do A minus 1 times A squared, you actually end up with A to this power, which is actually A. So we conclude immediately. You see that here A is equal to identity, and this is it. So the second, you have a nilpotent matrix. So namely, it's such that a to the power n is equal to 0 for some n, and it can't be invertible. So how do you argue here? Well, let's argue by contradiction, okay? So let's assume that it's actually invertible by contradiction. Assume A invertible. So that would mean, I mean, if you have the with inverse A minus 1, and there is something interesting here. If A is invertible, then A to the power n is invertible with inverse A to minus n, which means just A minus 1 to the nth power. This is very easy to check. In any case, you can multiply. You have this thing. You can multiply this A to the n to A times minus n, so this guy here, and you would get the identity matrix. But here you assume that this is the zero matrix, so you would conclude that the identity matrix is the zero matrix, and this is a contradiction. So it's okay, we're done. So, and the last one, again, take a matrix A such that A to the n is equal to 0, and then you still can find an inverse of this new matrix, I minus A, and the inverse is such, is this one. I mean, since here the formula of the inverse is given, we just have to make a computation and check that if we multiply I minus A with this other thing, so I plus A plus n minus 1, then it's actually the identity. And also if you multiply it at the other side. So let's try. So here you just the identity here, and then you have minus A squared, etc., minus A to the A n minus 1, and then you have minus A to the n, but this is 0. So you see that this cancels with this cancels with this, and so on, and you're left with the identity. On the other hand, if you do just this, it's actually the same thing. So again, here, precisely the same thing again. Then again, minus a, minus etc., minus a and minus 1, minus a the end. So again, this is 0, and this goes away, and you're left with identity. So, okay, you see here, the point is that you can multiply matrices just as they were ordinary numbers. You have just to be careful that the matrix multiplication is not commutative, but you don't use this, so it's okay. It's the matrix multiplication is really like multiplication of numbers, save for the fact that it's not commutative, but it's associative, and you can more or less you can do it as you were like multiplying numbers. I say again, just be careful that you don't have commutativity. So, for example, you can't say something like for matrices a squared plus b squared plus 2ab. This is very wrong. Instead, what is true is that you'll have a squared plus b squared plus ab plus ba, and ab plus ba will not be in general 2 times ab. They are not numbers, they are matrices, they are different. Okay, very good. We managed to to do every exercise, and now comes the part where we write down detailed solutions, as we know. So actually here I'm going to cheat a little bit, and I mean, it's something you can also do you can also do yourself. So in this case, you see that computing the inverse of this A matrix was very boring, and it was really just the Gauss elimination, and we've already written this. So in this case, let's say we don't want to lose a lot of time rewriting everything. Well, let's say we're pretty confident, we take this risk, we are pretty confident that our computation is correct, and the way it's written right here is not that bad. It's I mean, it's not perfect, but it's still not so bad. So let's take a risk here, and let's not rewrite it, and let's assume and let's hope that whoever reads it, they read this, and they look at this, and they can more or less figure out what is going on here. So they just read through this, and they can more or less figure things out. So let's see, we take this as the solution. We don't rewrite it, because we could, well, of course we could, but it would mean really a lot of time and a lot of effort, and we are just taking this risk. I mean, as I've always said, it's really up to you to choose what risks you take while writing things, especially in an exam. In this case, you can decide, well, it's very long, so I just hand in the copy of my draft. I just hand in my draft, and you can decide, well, it's not really that badly written, it's more or less understandable. So let's say that it's acceptable. Even better, what one could have done can be, well, we could have tried and write a nice and detailed solution from the beginning. So like here with some comments and so on. We didn't do this, but we could. And this is another thing which perhaps if you're confident enough with your computational skills, or also if you're not doing anything which is really tricky. Here there is nothing which is really tricky, and this is what actually tells you that even not writing everything really in a extremely detailed fashion. So I mean, placing comments here and here, saying more than like these things here. The actual idea of this computation is nothing strange. It's nothing very interesting. So you can take the risk and say, well, let's assume that it's enough like this, and let's keep this, because instead it would be very long to rewrite everything. And we decide that it's still understandable, it's still good, and it's still acceptable as a solution. In this case, that would be still, from the point of view, from my point of view, from a teacher's point of view, that would still be okay. Because, just to repeat again, the point here is that there is nothing really tricky here. It's just like start with this, and it's clear that we are going this, and we're starting with this, and then start with this algorithm, and then the passages are more or less described here. So it's a risk I'm taking here, but it's not really that bad. So in these cases where the procedure is really straightforward, and it's just computations and there's nothing tricky, it's acceptable that you still hand in your draft, or even better, you can try, if you're confident enough, to write down a detailed solution from the beginning. So let's accept that this is already a good solution, and let's continue from here. So let's add a page here. Or perhaps let's go on from here. So a minus 1 is this, okay. And now, well, here instead, well, let me see. Let me just, well, here I have problem of organizing pages. Let me see. So here's the draft. Here's the draft. Okay. Let's see that. Okay, let's assume that this is good. Let's say that we push the draft. In this case, we push it a little away. Yes. Okay. Or perhaps let's say this. Let's put the inverse here. Copy. Here, just organizing the. Unfortunately, this you can't do with the regular paper, but yeah, it's not too bad. It's not too bad, not too nice either. Okay, let me just do this for a moment. I'm just taking this. Okay. Now we can finally take this and put it here. Okay. This is pretty clear. This is already pretty clear. So if you want, like, do this, put it this way. Okay. This is already okay. And let's say, since we started with the with the detailed solution here, let me just add a page here and continue here, which is like, it's nicer. Now there is the second part, and in this case, for the BT matrix, I instead advise you to be a little more careful, because here it's not that straightforward as before, because you have this thing, and this has to be taken really carefully taken care of. So we chose to keep the old draft for this first part. That was okay, but for the second one, I will not take the risk, and I'll write down a more detailed solution for the inverse of this bt. And the reason is, this is important, the reason is that you have this tricky thing, you have this parameter, and you have to be careful at some point while dividing things. And I'm not taking the risk of reusing this draft here, because I think perhaps this is not very clear. So let's just rewrite it. And since fortunately it's easier, it's just a 2 times 2 matrix, so it will be easier. It won't be as long as the A matrix. So yes, we just do this. Very good. Let's start. So okay. Okay, let's see. Then sorry. If you want, just change this. We find the inverse using okay. So this looks nice, acceptably nice at least. We try and find bt, of course, if it exists, using Gauss. So consider so bt was this. Okay, so 1 t 1 true 1 1 0 0. Okay. Okay. So okay, so this, and 0. Okay, true minus t minus 1 1. Okay, here it's important we assume t is different from true, and divide okay, very good. So you get this 1 t 1 0 0 1 minus 1 over true minus t 1 over true minus t. Let's check if it's correct. Looks fine. Yes. Okay, and then we go on. Again here we replace the first with so it's the first minus t times the second, and you get what? 1 0 here. Okay, here you get 1 plus t, this fine, minus t this, and this stays the same, minus 1. Okay. So let's just compute here 2 minus t plus t, which is then 2 over 2 minus t. So we conclude if t is different from 2, the inverse of bt is given by bt minus 1 equal to let me see, 2 over 2 minus t, this is okay, minus t, 2 minus t, minus 1, 2 minus t, 1, 2 minus t. Should be okay. Minus t, minus 1, 1. There. Okay, very good. So, and we are left, of course, if t is equal to 2, then here, put a marker here, we get from so it's 1, 2, 1, 0, and 0, 0, 1, 1, minus 1, 1. Okay, and here, yes, we conclude that in this case bt is not invertible. Yeah, it's not. You see it. You see it here. You can't make the identity appear here. You're unable to do so. And then you can't go on. You simply can't go on with the algorithm. And from the theory, you should know that this means that you don't have invertibility in this case. Okay, and okay, so we're done with the first exercise. So this is a solution. We're not really done with everything. So there's the last part, still the second part. Okay, but here it's easy. A is invertible. Hence, the linear system Ax equal to b has only exactly one solution, which is given by x is equal to a minus 1 times b. So let's do the computation here. So let me just copy the matrix, this matrix. So okay, this is the inverse. So yes, and b was this, and then you just compute, and it is what it is. I mean, it was, yes, we've done it what was it? Minus 375, but now it's not really important even if you make a mistake here. It's not really an issue. It's not a problem. Very good. So this is for the first exercise, which was like not really hard, but kind of long and boring. But we made it. So fortunately, the following one is a little nicer. So okay, this is the second one, and let's write a solution now. We go, we put another page here. Okay. Let's be detailed using an inverse of A. So if you want 1 1 0 0, and then write like this if you want. I'm making this a little more compact because so you can just replace 3 true with true minus A times 1, and so this is it, minus A 1 1 0. Okay. So 1 minus A 1 0 is the inverse of 1 A 1 0. We then conjecture then that the inverse of this IP IQ A0 is given by IP minus A IQ 0. Indeed, IP IQ. Here you have to show that this is the inverse. So you have to make the multiplication using, of course, block multiplication. It's perfectly okay. And indeed, you find out that it's here 1. I mean, well, IP 0 0 IQ, which is actually the identity matrix IPPQ. And if you do the other way around, it's the same thing. Very good. So here and this is it. In order to show that some matrix is an inverse of another, you just have to multiply it in both ways and check that you get the identity matrices. That's it. You just a comment here. This part we could have just didn't. It was not really important. This could be also removed. I mean, I've put it just to like make the explanation even clearer. So here I could give you just this, and that would be this, just this. So just from this to this, that would be perfectly fine. But perhaps a reader could say, well, why did he decide that that this works? and from did he know it from the stars? I don't know. It doesn't look like very intuitive, but instead here you prepare the reader with like this easier example with a computation you can do right really mechanically. And hence if you have this part, then this part is nicer and it's more motivated. But it's not I mean, it's not something you really have to do. It's something you can do, and it makes the reading experience a little better perhaps, but it doesn't it's not really required. So in principle you could have just avoided this. You wouldn't lose anything any point in an exam if you didn't write if you hadn't written if you didn't write this this part. This is perfectly sufficient, and as I said, I remark again, this first part is just for the sake of like more clarity and a better experience for the reader, but it's not required. If you want to make the experience better, then okay, even better, but don't worry. We could have written just this part. Okay, I hope this is clear. Okay, let's go to the Hammond code and let's make it let's write a nice solution here. So let's go here. Fine. So okay, so we start. We observe that H is of the form H equal to A and the identity 4 by 4. This is 4 and this is 15. Hence, the generator matrix G is given by G. So this has to be like here, and you take A. So this is 11 and 4. Yes, this is 4, 11, 4, again 15. This is correctly 11. Indeed, G, if you do HG, then you can use block multiplication. Well, sorry, it's I4, I11, which is again you use block matrices. Yes, it should be okay. Yes. It's A minus A plus A, which is 0. Recalling that we are working with matrices over the field, the finite field 0, 1. So okay, so we don't have, of course, now we don't have to repeat the explanation I've given you before. So let's just we compute the syndrome, the so-called syndrome. Didn't tell you, but this vector here, HV, and yeah, you don't have to make the computation explicit here because it's very long and very cumbersome. So just copy the final result, which was 0, what is it? Yes, 0 1 1 1. Yes, I think so. Yes, 0 1 1 1, which is the fifth column of H. Hence, the correct decoded message is, and here just W, and you write it. What was that? Yes, let me just copy it because it's sorry, forgot. I'm going to forget this if I try and sorry. Unfortunately, you can't do these tricks on paper, but you can copy. Just to be really detailed, we've corrected the fifth figure. Can I say figure? The fifth figure. Okay. Well, let's say digit. And then you can say since G A, we deduce that the original message B, which satisfies GB equal to W, is given by the first 11 digits of W, namely B is equal to what it is. It is what it is. So yeah, let me just copy. Hopefully there are not mistakes here, but there shouldn't be. In any case, if there are some mistakes here, this is perfectly nice solution for this kind of exercise. It's very detailed, so yeah, you first say that you have this kind of block matrix. You find this generator matrix, and you see that this makes like this 0. And you recall that you are working on over the field of this just true 0, over the field of just 0 1, which is like finite field with two elements 0 1, and then you say we compute the syndrome and so on, and yeah, it's okay. This is a perfect solution for this exercise. So the last one, which is now proving stuff. So now it's really writing a proof. So A. So it's invertible. We know that let A minus 1 be the inverse of A. Then we multiply on both sides and find out A minus 1 A squared A. A minus 1 A is equal to the identity matrix by definition, and A minus 1 A squared is equal to A minus 1 plus 2 is equal to A. We conclude that A is equal to the identity as claimed. Okay, this is a nice proof. The second one, B. Okay, assume by contradiction that A is invertible. And let A minus 1 be the inverse of A. Then A minus 1 to the n is the inverse of A to the n. Hence, we obtain, you can write this, 0 is equal to A to the n. This you know. Just the 0 is equal to A is equal to, let's write this, 0 times A to minus 1 to the n is equal to A to the n, A minus 1 to the n, is equal to the identity. And I mean, you can see here that it's already, which is a contradiction. Hence, A is not invertible. Not invertible. Very good. And the last one, finally. So, you can see this. We compute I minus A and minus 1. This is equal to I plus A and minus 1, and then minus A minus blah 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 A n minus 1 minus A to the n. So, which is again I. You see it. You can also do like this to make things even clearer. And also the other way around. The same thing, actually. Just want to be really pedantic. And yes, here. Since say this here and here, okay, and so again here, here, here. This is very clear identity. We conclude that I minus A inverse is indeed this, given by this thing. Okay, that if, let's recall this, okay, let me just write it a little better. So here, okay, that if, okay, and this is it. This was just direct check, and we're done. We're done. Today it was a little longer than usual because of like kind of boring computations, but I hope that things are clear. So yeah, that was kind of reasonable, the last one, and yeah, and also the code. And I just remark again that in the first exercise I decided to avoid rewriting this first very long computation to save some time and some energy, of course. But it is still okay because like this kind of computations, I mean, there are no parameters, there is nothing, so they're pretty straightforward, and the way they're written, like here, they're still okay. So yes, okay, that's it for this time, and then well, think we'll see each other like in a few days with some